Hello, we were looking at the chapter on nitrogen compounds. First, we looked at the nitro compounds where the NO2 group is attached to a benzene ring. Sometimes the benzene ring may be attached with more than one NO2 group, and we have looked at the preparation of these nitro compounds. Then we spent some time on the reduction of nitro compounds under various conditions. What will happen with metal and HCl, metal and ammonium hydroxide, and various conditions by which the nitro compound is reduced to the amino compound and other compound, azo compound, hydrazo compound, etc. Today, after that, we looked at amines, this RNH2, ARNH2. The NH2 group is the functional group in these molecules, and the NH2 groups are basic because it has a lone pair of electrons, and this lone pair of electrons can be attached to the protons H plus, and the basicity of the amine is determined by the equilibrium where the amine plus H plus goes to the amine, protonated amine. And we looked at the various preparations of amines and also the reactions of amines. Now, we are going to look at a few special topics on amines which I have put in appendices. This is attachment to the main thing. They are not exactly in this syllabus, but it will help you to understand the chemistry of amines so that you can those who are interested can pursue more advanced topics in chemistry of amines. Now, this is the amines appendix 1. Nitrogen uses 4 sp3 hybrid orbitals which are directed to the corners of a regular tetrahedron like a carbon atom. So, this is how the ammonia molecule is there. This nitrogen is sp3 hybridized. The sp3 hybrid orbital is attached to this hydrogen. The second sp3 is attached to this hydrogen. Third, this hydrogen. One of the sp3 hybrid orbitals contains the lone pair of electrons, and hence this molecule, see, one side is the lone pair, all the 3 hydrogens are coming above the plane. This is a pyramidal compound, and this undergoes very fast exchange between the 2 pyramidal structures. One in which I have written the 2 structures. Here the hydrogen is coming forward, and this hydrogen is above and this hydrogen is below. This is in the plane of the ring, and the lone pair is on the opposite side. This is very similar to carbon compounds, where you have, say, in methane 4 hydrogens are attached, except in this case one of the hydrogens are removed and the lone pair of electrons is in the same place. So, in methane the carbon atom is tetrahedral. Here, since one of the sp3 hybrid orbitals is arranged attached to the lone pair, this is the pyramidal structure. That means this the tetrahedral structure is removed with this particular bond. So, these 3 bonds form a pyramid. The one of the locus of the pyramid is the lone pair of electrons. If you look at these 2 structures, one is a mirror image of the other. Normally, in carbon compounds, if you have a molecule which is a mirror image of the other molecule, and if they are not superimposable, if the mirror image is not superimposable, if you take this here, these two can be superimposed, but these two cannot be superimposed, and that particular carbon is optically active. The compound will rotate the plane of polarized light. But in this ammonia molecule, the two pyramids change rapidly. One pyramid becomes the other, very rapid thing, so that it is not holding this configuration where one atom is in the pyramidal place. This pyramid will become the other pyramid, and therefore this molecule is undergoing this change very rapidly, and it cannot be isolated as optically active isomers. If you have even nitrogen with 3 different alkyl groups, you expect it to be chiral, and A and B should be optically active. The previous 2 ammonia substituted with 3 alkyl groups, but such enantiomers have not been isolated. Even with 3 alkyl groups, the energy barrier for conversion of one pyramid to another is small. So, the conversion of the 2 pyramids is very fast, and therefore, it does not hold the configuration, and it does not give optical activity, or it is not superimposable, because they keep changing so fast. But if you have an ammonium salt where the nitrogen is attached to 4 different alkyl groups, methyl, ethyl, propyl and benzyl group. This particular molecule, if you see that they are not superimposable, and the energy barrier for conversion is very large, therefore, they do not interconvert from one pyramid to another pyramid. The rate of interconversion is very slow, non-superimposable, therefore, it is optically active. In such molecule, the optical isomer has been isolated, and they have been shown to have rotation. That is, they rotate the plane polarized light to the right or left, depending upon which molecule is isolated in the 2 mirror images. Then we look at the appendix 2, which is Hoffman elimination. If you have dehydrohalogenation of an alkyl halide with alcoholic KOH, usually the molecule splits up HX, and this splitting of HX, the removal of HX, can take place from this hydrogen and this X, or this hydrogen and this X. If the reaction is done by alcoholic potassium hydroxide, you get CH3, CH, double bond CH, CH3. That is 2-butene. This is formed to the extent of 80%. That means alcoholic potash abstract this particular hydrogen. So, let us say if there are So, this is the process by which hydroxide picks up hydrogen here as proton. This will form a molecule of water, and this bond moves to between the 2 carbons, then this gets out as X minus. So, this is CH3, CH double bond CH, CH3. This is 2-butene formed at 80%. This is a more stable olefin or alkene. Now, some of the product is formed by removal of this hydrogen, and just like this, the bond moves here, and then the X minus leaves, and you have 1-butene. When this hydrogen and X moves. This is the CH double bond CH2. This is one butene formed to the extent of 20%. The outcome of this reaction, in which more substituted alkene, which is also more stable, predominates, is called the Zaitsev orientation. When you have an alkyl halide treated with alcoholic KOH, you get what is called dehydrohalogenation reaction. This dehydrohalogenation takes place preferentially to get the more stable alkene. The more stable alkene is the more substituted alkene. If you have two substituents to this carbon, two substituents to this carbon, so this is more substituted carbon. The other alkene is formed at 20% yield. You now see this carbon has an alkyl group. This carbon has two CH2 group. So, the number of alkyl groups on the carbon is 1, here it is 2, here 1 and this 1. So, when it is less substituted, the alkene is less stable, and this is formed only to the extent of 20%, and this type of dehydrohalogenation, where the more substituted alkene is formed in greater amount, very large greater amount is 80%, versus the less substituted alkene, this is formed to the extent of 20%. This is called Zaitsev orientation. This is a scientist who first discovered this dichotomy, where one olefin is formed in greater extent than the other olefin, and that olefin is more substituted olefin, the one that forms in greater amount. So, this particular orientation of the double bond, here the orientation is between 2 and 3, here it is between 1 and 2. This orientation is called Zaitsev orientation. When the following tetraalkyl ammonium hydroxide is heated, an alkene is formed. This is the tetraalkyl ammonium hydroxide. You have 4 C2H5 group attached to this nitrogen and 1 propyl group attached to this nitrogen. When 4 groups are attached to the nitrogen, it forms an ammonium salt, a positive nitrogen, and this, when you heat it, the counter ion here is hydroxide. You have already formed O minus, this counter ion is OH minus, this is N plus. In this, if you heat it, this hydroxide abstracts the proton here, the bond moves between the two carbons and removes this nitrogen compound as triethyl amine. So, you get triethyl amine and water and also alkene. So, this alkene is more substituted and you form this alkene. Actually, here there is no difference whether you move this particular thing or the other compound, you get the same 2 alkene. Now, let us see the orientation in Hofmann elimination when 2 different alkenes can be formed. Here only 1 alkene can be formed, this abstraction of this. If you abstract here, there is no leaving group. So, other alkene cannot be formed here. So, only this hydrogen can be removed by hydroxide. When this hydrogen is removed, then that cannot move and remove the triethylamine. Now, when the orientation of the Hofmann elimination, when 2 different alkenes are formed, now you have the same type of NR3 plus, the trialkylamine, there is a 4th alkyl group, this is 2 butyl group. So, 3 alkyl groups plus 1 more alkyl group, 4 alkyl groups, then the nitrogen becomes plus. Then OH minus is the counter ion, and if you have the, if you heat it, this hydrogen can be removed from here to form an anion, and that can move and remove this, can come down to here and then move the trialkyl amine. So, this is the intermediate. You have a carbanion formed which moves to form a double bond, and then the trialkyl amine is formed. The molecule of water is formed because this OH minus abstracts this hydrogen to form the anion. Now, this particular anion is more stable. We will compare it with here. Now, you do the elimination making this carbon anionic. You here OH minus abstract this hydrogen from this carbon. Here it abstract hydrogen from this carbon. So, this is the anion. So, this anion is formed by abstraction of this hydrogen, and it again moves in to form a carbon-carbon bond, gets the trialkyl amine out, and you get the more stable 2-butene. And here the product is 1-butene, which is less stable. And actually, in Hoffman elimination, this product is formed this is formed in greater amount, this is formed in lesser amount. This comes from the fact that intermediate to this is this carbanion, which is substituted with only one carbon. Carbon is electropositive, it pushes the electron into this bond. This CH2 minus is somewhat unstable, but of the two, here you have two alkyl groups which push the electrons. This carbanion is less stable, and the resulting 2-butene is more stable, but in this case the reaction is determined by the stability of anion. This anion here determines that the product formed here is more, though the product is less stable. Here the product formed is less stable, it's more stable, less stable intermediate. Formed in greater amount. This is formed in lesser amount. This is because this anion is more stable. So, most of the product results from this anion. This anion is less stable, less of the alkene is formed from this carbanion. Now, you have unit 4b appendix 2 continuation. This Hoffman elimination takes place via a more carbanionic intermediate, which is more stable as it is formed by the abstraction of hydrogen from a primary carbon. The abstraction of hydrogen from a secondary carbon is sterically hindered and also results in a less stable carbanion. Stereochemistry may be anti or syn depending upon the steric factors. The stereochemistry, if you have this compound, there is no stereochemistry associated with this, because this is CH2, whereas here you have two possible this is cis, and you can have trans. The two methyl group opposite to each other is trans, and that stereochemistry is depending upon the structures and the steric hindrance as well as stability of the carbon ions. Now, there is a similar reaction which is called a Cope elimination. It starts from this nitroso compound N plus nitrogen, the amine is treated with the NO. This forms the nitroso compound. This N plus R2. When this can abstract this hydrogen in a cyclic fashion, this hydrogen is abstracted. This bond goes towards the two carbons, and this bond from it goes to neutralize the Nr2 plus. You will get Nr2 plus dihydroxylamine, dialkyl hydroxylamine. Dialkyl hydroxylamine. So and the olefin is formed by between the two carbon atoms. This is a syn elimination because the two hydrogen and Nr2 plus is on the same side. These therefore, this elimination is syn. If you have groups here which are different, you can detect whether the product that is applied is syn or trans. Now, you can see on heating suitably substituted amine oxide, an alkene and dialkyl hydroxylamine are formed. The intermediate is cyclic as shown. You have a cyclic intermediate, and the reaction gives products only by syn elimination. That means, these two hydrogens and this Nr2 plus are from the same side of the molecule. So, if I write the reactant like this, where the CH group and this Nr2 plus group are on the same side, and the two methyl groups are on the same side, two hydrogens are on the same side. If it goes by a cyclic intermediate, the product formed will be cis-2-butene. But if you prepare an isomer where the CH3 and CH3 group is opposite side, and you have all these groups attached, when the reaction takes place, it goes via the cyclic intermediate. The cyclic intermediate vandaka inge vandu trans 2-butene varum. The trans 2-butene vandu இதுக்கு ஆப்போசிட் டைப் ஆஃப் ஸ்டீரியோகெமிஸ்ட்ரி. இந்த டிரான்ஸ்பியூட்டின் வந்து இந்த மாதிரி இந்த சப்ஸ்டிடியூவன்ட் CH3 ஆன் தி சேம் சைட், இந்த CH3 மற்ற ஆப்போசிட் சைடில் இருந்தாக்க இந்த மாதிரி trans 2-butene வரும். ரெண்டுலேயும் dialkyl hydroxylamine will be formed. இந்த அப்பெண்டிக்ஸில் டயசோனியம் சால்ட் அதோட ரியாக்ஷன்லாம் பற்றி எழுதியிருக்கு. இந்த டயசோனியம் சால்ட் ஃபார்ம்ஸ் எ வெரைட்டி ஆஃப் குரூப்ஸ், வெரைட்டி ஆஃப் காம்பவுண்ட்ஸ். அது நிறைய சப்ஸ்டிடியூன்ட்ஸ் ஆட் பண்ணலாம். அதை வச்சுட்டு ஃபர்ஸ்ட் இது வந்து சாண்ட்மேயர் ரியாக்ஷன். இட் இஸ் நேம்ட் ஆஃப்டர் தி டிஸ்கவரர் ஆஃப் திஸ் ரியாக்ஷன். இங்கே வந்து ArN + triple bond NX-. This is the aromatic diazonium chloride. இந்த diazonium chloride cuprous chloride ஓட react பண்ணாக்க you get ArCl, chlorobenzene or chlorotoluene etc. So, இந்த diazonium salt if you react with cuprous bromide, அது வந்து ArBr கொடுக்கும். The Ar can be phenyl, substituted phenyl. இதையே வந்து பொட்டாசியம் அயோடைடோட ரியாக்ட் பண்ணாக்க ArI, benzene attached to iodine atom. இந்த ஃப்ளூரின் ப்ரிப்பேர் பண்ணாக்க அது வந்து வேறு இன்டர்மீடியேட்டோட போகணும். இதை வந்து ஃபர்ஸ்ட் யூ react with HbF4 tetrafluoro boric acid, and this is tetrafluoroborate ArN2 plus Bf minus, it's called fluoborate, and this when heated produces ARF. இது வந்து இந்த நைட்ரஜன் இவால்வ் ஆகிடும். BF4 ஒரு ஃப்ளூரின் மாத்திரம் இந்த aromatic ringல attach ஆகும். You get ARF. In all these reactions வந்து nitrogen gas will be formed. It goes out. Therefore the reaction will be shifted. முழுக்க இந்த ArCl இந்த பக்கம் வந்துடும். There is very little left of the diazonium chloride. Now in the reaction la aromatic diazonium chloride react with cuprous cyanide. இதே மாதிரி cuprous, you have halogens attached. Now cyanide group also gets attached, ArCN plus N2 gas. The diazonium chloride with water and heat you get phenol, ArOH. இது முன்னாடியே phenol preparationல பார்த்துருக்கோம். ArN plus triple bond NX minus with H3PO2. It's a reducing acid derived from phosphorus. H3PO2 plus H2O. இதை react பண்ணாக்க இந்த bond is reduced with hydrogen and you get ARH, and here also you get N2 as the byproduct. So appendix 4 la analysis of amines, especially this test is called Hinsberg test. The test is used to identify whether a given amine is a primary amine or secondary amine or tertiary amine. இது எப்படி பண்ணுறதுனாக்க இந்த அமீன்ஸை வந்து பென்சீன் சல்ஃபனைல் குளோரைடோட ட்ரீட் பண்ணுறது in the presence of aqueous potassium hydroxide. பொட்டாசியம் ஹைட்ராக்சைடு வாட்டரில் டிசால்வ் பண்ணி சொல்யூஷன் பண்ணிட்டு இந்த அமீனை வந்து பென்சீன் சல்ஃபனைல் குளோரைடு போட்டு இந்த ஏக்வஸ் பொட்டாசியம் ஹைட்ராக்சைடை அதில் ஆட் பண்ணுறது. இதில் வந்து பிரைமரி அண்ட் செகண்டரி அமீன்ஸ் ஃபார்ம் சப்ஸ்டிடியூட்டட் சல்ஃபனமைட்ஸ். இங்கே பார்த்தீங்கன்னாக்கா RNH2 plus C6H5SO2Cl will form RNHSO2C6H5. இதில் வந்து one hydrogen here has been replaced by C6H5SO2 group.